Alright, section 2.4, properties and proofs. The most important skill we learned in algebra last year was how to solve an equation. When we solve an equation, remember the golden rule. What you do to one side, you must do to the other side. Each time you complete a step, we're actually using a property of equality. Now in algebra, we didn't have to explain each of these steps in words, but in geometry, we have to give a reason for the steps we take. So when we look at this chart below, we have our algebraic property, which is the addition property, our example. What we can do with the addition property is we would say plus 3 and plus 3. So we'll get x minus 3 plus 3 equals 10 plus 3. And then getting a little fancy, we can use letters. So if a equals b, then a plus c is equal to b plus c. What it means is we're adding the same number to both sides. So we're adding the same number to both sides. And like the addition property, the subtraction property, we have x plus 5 equals 23. Well, we can do x plus 5, and we can do minus 5, and 23 minus 5. Getting a little bit fancy here. Well, if we have a equals b, then a minus c equals b minus c. What that means is we're really just subtracting the same number from both sides. And we subtracted 5 from both sides there. And then we were able to do that because of our subtraction property of equality, where whatever we do to one side, we do to the other side. Now with the multiplication property, well, if x divided by 6 equals 3, well, we want to multiply this side by 6, multiply this side by 6, so that we get x equals 18. So we can multiply both sides by 6. Well, once again, getting a little bit fancy with our letters, well, if a equals b, then AC is going to be equal to BC. Well, what it really means is we can multiply both sides by the same number. And then with the division property, we have 4x equals 20. Well, we can divide this by 4 and divide this by 4. So we will get x equals 5. Getting a little fancy, well, if a equals b, what we can do is a divided by c is equal to b divided by c. Now the thing about c cannot equal 0, well, we can't divide by 0, so we have to put that stipulation in where we just can't divide by 0. So what this means is we can divide both sides by the same number. As long as we're doing it to both sides, it's okay. Divide both sides by the same number. So our substitution property, well, if x plus 3 equals 10 and y plus 3 equals 10, we can say that x equals 7, y equals 7, so x equals y. Well, if a equals b and a equals x, then b equals x. So getting a little fancy is, what we can say here is we're replacing the quantity of we're replacing a variable with a known quantity. So we're replacing our variable with a known quantity. Well, if a equals b and a equals x, so we are taking out a and replacing it with x. So we're just taking this x and putting it in for a. So that's all we're doing. Substitution property. So we're just replacing our variable with a known quantity. The next three properties, it's all given there. The reflexive property, it just says, well, if a equals a, then it's reflexive. So we have our congruencies. Well, a is congruent to a. Well, this figure has to be congruent to itself. The symmetric property, well, if a equals b, then b also equals a. So if a is congruent to b, then b is congruent to a. So if a is congruent to this figure, that just means this figure is congruent to this figure. And the transitive property, well, if a equals b and b equals c, then a equals c. This is kind of like our logical chain. If a equals b, then b equals c, And if so our logical chain, we're going to get down there. So A has to equal C, and our visual, well, A is the same as B is the same as C. Well, A and C have to be the same thing. Now, something we're going to start to talk about are proofs. In order to complete a true proof, this example will be written in a 2-column format. Alright, this 2-column proof will be used most often when we study and continue on with proofs. We build our argument on the left and we give our reasons on the right. So the first step in any proof is called the given. Any statement we're given, we put it first and our reason we're given that statement. The last step is our conclusion. We will always be given a conclusion. So this is what we want to prove. So in this equation, we're given this equation and we want to prove that x equals 10. Well, the first thing we want to do is when we look at it, well, we notice we have x on both sides, so we want to get rid of them. So what we can do is subtract that 2x from both sides. Now the reason I'm allowed to do that, that's my subtraction property. So that's my subtraction property, because I subtracted 2x from both sides, so they're going to cross off, and then 4x minus 2x, that's going to give me 2x, so I have 2x minus 7 equals 13, so my subtraction property allowed me to do that. Now what I just did there was I simplified it. So we simplified, we did 4x minus 2x, and we cross off these x's. So now I have 2x minus 7 equals 13, I want to get x all by itself, so I actually want to add 7 to both sides, so I want to do plus 7. And what allows me to do that, that's our addition property. So that's our addition property. Now we all remember how to solve these, so we're starting to get in that habit of giving the reasons for what we're doing. Our 7's cross off, so we have 2x, 13 plus 7 is 20. So we simplified it again. So we simplified it, and now to get x all by itself, we're going to divide by 2. So it's going to be 2x divided by 2 equals 20 divided by 2. And what allowed us to do that? That's the division property. So the 2x, the 2's are going to cross off, and we'll be left with x, and 20 divided by 2 is 10. And we simplified to get there. Alright, so we simplified to get there. So that's developing a 2-column proof. We have our statements on the left side and our reasons for doing everything on the right side. Now, the next thing we're going to be talking about is the overlapping segment theorem. So it says in this figure, the lengths of A, B, and CD are equal. Well, what can we conclude about the lengths of the two overlapping segments? AC and BD. Well, this is 4. This is 4. Well, BC and A and BC have to be equal to each other. They're both 5. So AC is going to be 9 units and BD is going to be 9 units. So these are equal. Now, any idea which property demonstrates this? Well, what we get here is what we're doing is we are taking AB, which is 4, and we're adding 5 to it. Then we had CD, which was 4, and we're adding 5. So since we're adding 5 to both sides, that's our addition property. So the property we're really using is the addition property because we're adding 5 onto both sides of these. So now it says we have this figure AB equals CD, and we want to prove that AC equals BD. So the statements, well, the first thing we always do is we write down what we're given. So we're given this AB is equal to CD. Our reason, it's given. Now we want to get all the way down to AC equals BD. Well, we're given that this is congruent to this. Well, what else do we know about that? Well, we know that this middle part, BC, well, we can add it to AB. So we can do AB plus BC, and we can do CD plus BC. So we can add it to both sides. So we can add it to both of those sides. And why? That's our addition property. Now, what else do we know about this? Well, if you look at it, well, AB plus BC, that's going to give us what? AB plus AC, or AB plus BC, that will give us AC. The reason? You have to think back to the last unit. That's our segment addition postulate. That's when we add the two segments together to get the entire segment. So AB plus BC equals AC. And then we can do the same thing where we have CD plus BC. That's going to equal CD plus BC. That'll equal the entire thing, which will give us BD. Once again, that's our segment addition postulate. It's going back to Unit 1 now. And once we get there, well, we know that AC is equal to BD. Why? It's our substitution property. What we did is we took AB and we plugged AC in for AB. And we took CD plus BC and we plugged it in right there. So we substituted those values in for each other. So that's how we can prove the overlapping segment theorem. Now, with the overlapping segment theorem, if AB is equal to CD, then we know that AC is equal to BD. So if AB is congruent to CD, this entire thing is congruent to this entire thing. And if it's the opposite, if we know that AC, the entire thing, is equal to this entire thing, that AB is equal to CD. And that is our overlapping segment theorem. Now tomorrow in class we're going to work on those examples and then get into the overlapping angles theorem.